Hello students, welcome to IMS GATE Academy. I'm Amit Goyal. I'm GATE CS mentor at IMS GATE Academy, and we have taken at least 3 sessions. In the last 3 sessions that we took on theory of computation, we have discussed basically the introduction of the subject, and we have also talked about the applications of the subject in the first session that we took. In the second session, we introduced the concept of deterministic finite state automata, and we did some of the questions on that. In the last session, what we did is, in the third session, which was the last session, in which we discussed some more interesting questions on DFAs. And today in this session, we'll be taking some more advanced questions on DFAs, and thereby we will complete the topic of deterministic finite state automata, right? So I hope all of you are attending my sessions and are understanding the concept of DFAs. And as I said earlier also, this is one of the most important topics which is asked in the GATE exam. You will there is a very high probability that there will be a question on deterministic finite state automata in the GATE exam. And if you practice all the questions which we do here, then there is a very high probability, there are very high chances that the question that comes in the GATE exam, you will also be able to attempt that, and you will get full out of full marks in that question, right? So let us start with some more interesting questions on deterministic finite state automata. Let's start with, again, today's session will also again start with the question only, right? So here goes the question. So let me briefly, so this was the homework question which I gave in the last session, and it goes something like this. So let me briefly explain the question, then I'll give you some time to solve it, and then we will discuss the solution also. Just a second. Yeah. So let us read out the question first. So the question says, construct a minimal DFA. Again, the minimal DFA. Why minimal DFA? Because we want the DFA which has less number of states than any other DFA which can be made for the same language, right? So construct a minimal DFA for the given language, and the language is given to you as W belonging to A comma B star. That is, W is a subset of sigma star, right? And what is being asked is, number of A's in W mod 3 is greater than or equals to number of B's in W mod 3. Now this becomes an interesting question, and we always also discussed in the last session that there are 3 ways of solving it. One is, you can go by the intuition that how many states will be there and then try to write the transitions, right? Second method is, you can go by the method of intersection, right? And then the third method is basically use the web DFA approach. We saw that such kind of DFAs that are coming, they all have a structure similar to the web DFA which we have discussed, right? So when the web DFA works, when we have number of A's mod something, number of B's mod something, right? In these two situations, what will happen is, when we have this kind of a situation wherein we have two symbols, mod of the two symbols, then we can use the web DFA approach, right? Which we discussed in the last session, that we'll change A's along the rows and we'll change B's along the columns, right? Something like that can be used as we discussed in the last session, right? So again, so now somebody can ask her, does the web DFA approach works also for three symbols? Like for example, if there is a condition on number of C's also, does it work there? Yes. In that case, the web DFA will be a 3-dimensional DFA, right? The 3-dimensional web will be there, and you can still use the same concept again to solve such kind of questions, right? But again, in general, it's tough to imagine a 3-dimensional web or a 4-dimensional web when we'll have 4 variables, right? So in that case, in generally, these questions are not coming in the exam. The only up to web DFA, a 2-dimensional web, that is coming in the exam, right? But still, if it comes in the exam, if you have a 3-dimensional web or a 4-dimensional web, that also you can solve based on the intuition that I have given to you, right? I hope this point is quite clear to everyone. So now let me give you some 2 minutes to solve this, and then we will discuss the solution in detail. Yes. So the condition is, number of A's mod 3 is greater than or equals to number of B's in W mod 3. That is the condition. I said that the number of A's in W mod 3 should be greater than equals to number of B's in W mod 3. That is being said, right? So when we say number of A's in W mod 3 is greater than equals to number of B's in W mod 3, what should be the situation here? So when I say number of A's in W mod 3 is greater than equals to number of B's in W mod 3, what you can see is this DFA has requirement of 3 positions, 3 states, that the remainder can be 0, remainder can be 1 and the remainder can be 2. Similarly, this DFA also has 3 states. Your remainder can be 0, your remainder can be 1 and your remainder can be 2. That is number of A's in W mod 3 and number of B's in W mod 3, right? Now, as we discussed, to solve such kind of questions, you have some 3 approaches as we discussed in the last session. What are the 3 approaches that we had discussed? One is you can think about all the cases in your mind and then draw the DFA to represent all those cases. That will become tough because you have to think about all the cases. Now, when we move to the next session, next way of solving this question, the another way of solving the same question was, what you can do is, you can take the intersection of the 2 DFAs. You draw this DFA first, then you draw this DFA, and then you try to take the intersection of the 2 DFAs. That is also a feasible approach, right? That can also be done. Now the third approach is, so first approach you understood, you can think about all the cases and then try to draw the DFA. Now once you have, so this is one approach which you can follow, right? If you cannot follow this approach, there is another approach wherein you can take the intersection of the 2 DFAs by drawing the 2 DFAs separately. Now the third approach is the web DFA approach, wherein you can make a web in which you will either take A's along the rows and B's along the columns, or B's along the rows and A's along the columns, right? So that approach we discussed. And again, now somebody can ask that, sir, whether this approach works on, approach works on other kind of DFAs wherein we have more than 2 variables, where we have more than 2 symbols. For example, C is also there in the string. Yes, it will work. In that case, your DFA will be a 3-dimensional DFA. Earlier you had 1-dimensional DFA, now you will have a 3-dimensional DFA in this case, right? So over here, if we see, there are 3 possibilities. Your remainder number of A's mod 3 can be 0, 1 and 2. Number of B's in W mod 3 can be 0, 1 and 2. So what are the overall possibilities? 0, 0, 0, 1, 1, 0, 2, 1, 0, 1, 1, 1, 2, 2, 0, 2, 1, 2, 2, right? So when you say all these things, you can see that in this case, we want that the number of A's in W mod 3 should be greater than equals to number of B's in W mod 3. Now if you see this example, if you see all these states which are representing number of A's in W mod 3 followed by number of B's in W mod 3, you have to make that this should be greater than equals to this. You have to make that this should be greater than equals to this. How will you solve it now? Now when it is greater than equals to this, if you say this, so 0, 0, number of A's is equals to number of B's. 1, 0, again number of A's is equals to number is greater than number of B's. Here it is equal, here it is greater, here it is greater, here it is equal. So 6 states are having acceptance out of the total 9 states. So we'll have 66.67% states which are final out of the total number of states. So there are total states are 9 and the number of final states are only 6. So what percentage of states are final? That is 66.667%, right? So this is basically what we have discussed in this example. This was the homework question for you guys, right? And now somebody can ask me whether you can draw this DFA also. Yes, definitely we can draw this DFA. How will we draw this? This is how we can draw this DFA. So basically, if you see this DFA, 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2, 2, 0, 2, 1, 2, 2. Now what I have done is, along the rows I have changed B's, along the rows I have changed B's, along the rows I have changed B's, along the columns I have changed A's, along the columns I have changed A's, along the columns I have changed A's, right? And now if you see this, we knew that out of that 6 states are final. 1, 2, 3, 4, 5, 6 states are final. This is how you can solve such kind of questions in a faster way. In fact, before I drew this DFA, you did not even have to make this DFA. Before drawing also, you can answer this question that how many states are final by just enumerating the states. You don't even need to draw this DFA to solve this. But if you want to draw the DFA, so this is how the DFA will be made. Now somebody can ask me, Sir, what are the number of transitions here in this DFA? Even for that also you don't need to draw the DFA. How you will get the number of transitions? Very simple. That is, there are total number of 9 states, and on every combination of Q cross sigma you have to write a transition. So Q cross sigma. So 9 over here, and sigma is nothing but A comma B, so you will get 18 transitions. So number of transitions will be 18 in this case. Is it okay, everybody? Yes? So I hope this much point is clear to everyone. Yes? Right? So let us move to the next question. Let us try to understand the next question. So this is a very, very interesting question, and if you know the technique of the web DFA, you can directly attempt these questions. You don't even need to draw the web DFA, right? Yeah. So let's come to the next one, which is a very interesting question. It says that construct a minimal DFA which accepts set of all strings over sigma equals to 0, 1, which when interpreted as a binary number is divisible by 2. So when we say which when interpreted as a binary number is divisible by 2, how do we read this question? So what is being said is sigma is 0, 1. So when my sigma is 0, 1, I can simply say that I will get a binary string. When that binary string is converted to the decimal conversion, when we do the decimal conversion of that binary number, we'll get 4. For example, if I take this binary string 100, I will get the number 4. Now 4 when divided by 2 is divisible by 2. So therefore it should be accepted. Now let's take one more example. Let's say my binary string is 101. In this case, what I will get is 5. 5% 2 is nothing but 1. 5 modulus 2 is nothing but 1. So it is not divisible. So this is accepted and this is not accepted. Is this point making sense to everyone? So this is accepted, this is not getting accepted. Right? So you have two cases over here. Right? So now you have to draw the DFA to see what will be the final DFA, right? So what is being said is construct a minimal DFA which accepts set of all strings over sigma equals to 0, 1, which when interpreted as a binary number is divisible by 2. So what is being said is, when we represent this number as a binary number 0, 1, sigma is 0, 1, I get a binary string. That binary string should be divisible by 2. So how should we solve such kind of questions, right? So that is an important point, right? So how should we approach this, right? So let me give you a hint here. Let us discuss a brief theory. So although what we understand is, if the number ends by 0, you take any binary number, if it ends with a 0, then it is divisible by 2. If it does not end with a 0, then it is not divisible by 2. So using that concept, I can simply draw this DFA. So what I can say is, so it is just like making the DFA for ending with 0, then we'll get the answer, right? So let's try to draw the DFA. So initially we are at Q0. If we get a 0, then we go to the, let's say, final state. As long as you are getting 1, what is being said is, which when interpreted as a binary number is divisible by 2. So let us assume that epsilon is also there in the language. Let me redraw it. If I am getting 0 only, then I will accept it. Epsilon, let us assume that epsilon is divisible by 2. Although it doesn't make any sense, but that is the assumption behind this question, right? Although it makes sense also, because if nothing is there, it can be assumed to be 0 and it is divisible by 2, right? Now when we get a 1, we go to Q1. If we get a 0 again we'll come back to the same state. If we are keeping on getting 1, we'll remain there itself. Now Q0 is representing over here. What is Q0 representing here? Q0 is telling you the modulus is 0. That is divisible by 2. and here the modulus is 1. When you are dividing something by 2, the only two possible remainders are 0 and 1, which have been represented in this DFA. The two possible remainders are 0 and 1. Now you see any binary number, if you are getting 1 and 0, 1 0 is divisible. If you are getting 1 0 0, again it is divisible. 1 0 1, not divisible. 1 0 1 0, that is 10, that is again also divisible. So it is just like saying that ending with, your number should end with a 0, right? If it is ending with 0, we are accepting. If it is not ending with 0, we are not accepting, right? So this DFA is very similar to saying that it is ending with 0. Are you getting my point? Yes. And this is assuming that epsilon is there in the language. If I say that epsilon does not belong to the language, how will my DFA will look like? It will look like something like this. So if epsilon is not there in the language, once you get a 0, you will assume that you have reached the final state, and your Q1 will become your final state. Now if you keep on getting 0, you will remain over here, but once you get a 1, there will be a problem. And if you are in the beginning itself, you are only getting 1s, you will still be having an odd number. Now this is also the same DFA for the same example. So both these DFAs are correct, 100% correct. Both these DFAs are 100% correct, right? Now this DFA is assuming that epsilon belongs to the language, which assumes that epsilon is nothing but a 0, nothing is assumed to be equivalent to 0, that therefore it is divisible by 2. Now here it is does not, here epsilon belongs to the language, here epsilon does not belong to the language. Right? So the idea was very simple, it must end with a 0 to be divisible by 2. But this was simple. Now in this case, if I say that which when interpreted as a binary number is divisible by 3, now what to do? Right? So let me take you back. Over here we had which when interpreted as a binary number is divisible by 3, which is divisible by 2. Now if I change it to something like this, which when interpreted as a binary number is divisible by 3, then what should I do? How should I solve this question? This is what we are trying to discuss. Now again, let me read out the question loudly and tell you what exactly needs to be done. So what is being done is, construct a minimal DFA which will accept set of all strings over sigma equals to 0, 1. Again, the binary strings which when interpreted as binary number is divisible by 3. So what are we trying to do? Sigma is 0, 1, you will get some binary strings. So let's say one example of binary string is 1010. 1010 when divided by 3, what does it give? So 1010 is nothing but 7. 1010 is nothing but 10. Now 10 when divided by 3 will give you a remainder of 1. Right? Now let me take it 1011 is nothing but 11. 11 when divided by 3 will give a remainder of 2. Now what is the next number? 1100. 1100. That is 12. 12 when divided by 3 will give you a remainder of 0. So this number should take you to the final state. This number should take you to the final state. Right? So what is being discussed here? We have 1010, we have 1011, 1100, 1100, 1100 is acceptable, others are not acceptable. Right? So what is the idea behind this? The idea is very simple. We will have 3 states. Why 3 states? To represent the 3 remainders. So when something is divided by 3, you can get 3 possible remainders, 0, 1 and 2. Based on that, you will have some 3 states in your DFA, Q0, Q1 and Q2. Q0 will represent remainder 0, Q1 will represent remainder 1 and Q2 will represent remainder 2. and through that logic you should try to solve this, right? And then keep on taking the strings. By taking the strings you will get to know what is it that I am going to get. Keep on taking the strings, right? And then keep on constructing the DFA, right? You know the meaning of each state. So okay, so let me give you 2 minutes to construct this. I have given you the hint, you should be able to make it, and then we will discuss a short trick to solve these types of questions within less than 1 minute. Even you can solve such questions within less than 30 seconds also, right? But let us do it in a traditional way first, and then we'll discuss the short trick. The traditional ways is you have 3 states, you know, given a binary number, you know whether it is divisible by 3 or not, you keep on making the DFA and keep on populating the transitions, and then finally you will get the final DFA. The other approach is a trickier approach. The trick we will discuss once you do the traditional approach, right? Please solve it using the traditional approach first. So before I give you the timer, just to make this point clear, how do you interpret a binary number? So for example, 1100, one of the ways of representing this is 0 multiplied by 2 raised to power 0, 0 multiplied by 2 raised to power 1, 1 multiplied by 2 की power 2, and then 1 multiplied by 2 की power 3. What is this? 0 plus 0 plus 4 plus 8, you are going to get 12, right? ठीक है? So you are getting 12 here. So now so this is one approach of converting a binary number to the decimal number. Now what is the other approach which will be useful in this? But now this approach is not very useful for us. Why? Because for this approach you have to calculate the number from, you have to read the number from left to right, from the least significant bit to the most significant bit, but this will not be the case in general, because the number will come from the most significant bit. The stream will come like this, 1100. So you will not be able to use the DFA directly, because you cannot wait until the entire string is with you. On every symbol of the string you have to take a transition. You cannot wait till the last symbol is coming, right? Are you getting my point? So you cannot wait till the last symbol is coming to you, right? So in that case we have to find out an approach which can start interpreting the number when the number from the most significant bit itself. So what is the approach? You have 1100, you take it as 1, you take the first one, that's it. Then after that, whatever you have got in the earlier step, you multiply it with 2, because the base is 2 for a binary number. Then you take the next number. What you get is 2 into 1 is 2 plus 1 is 3. Now whatever you got in the last step, you multiply it with 2. Then you add what is given to you. You get 6. What you got in the last step, you multiply it with 2. Then you add the next number, that is 0, you will get 12. So this approach also gives you 12. But in this question, which approach will be useful? This one, because the number will be given to you, from MSB to LSB. That is the most significant bit to the least significant bit. So you should use this approach rather than this one. Although both are correct, but the number will be given to you from MSB to LSB, not from LSB to MSB. So that is why you have to use this approach, right? Now you have all the necessary information to solve this question. What is the information that you require? You require that you have 3 states, because number is being divided by 3. 0, 1 and 2 are the 3 states that you require. One information. Second information that you have with you is how to convert a binary number at runtime into a decimal number. And based on that, you can start approaching this question, right? So just approach this question in the next 2 minutes, and then we will see the solution. So apply this approach on this question, and then you will see the solution in detail. Okay, the time is up. Is anybody able to solve this? Okay, so let's see the traditional approach first, as I said, and then we will discuss the short trick also. So if you go by the traditional approach, initially we will be at Q0, then we'll go to Q1, then we will go to Q2, right? Now understand this point, that initially we are assuming that epsilon Q0 is representing remainder 0, Q1 is representing remainder 1, Q2 is representing remainder 2. And initially epsilon also we are assuming that it is a part of the language, because epsilon can be interpreted as 0, that is absence can be interpreted as 0, and that is the assumption that we are taking, and therefore we are keeping Q naught also in the system, epsilon also in the system, in the language. Now if a 0 comes, you will stay here itself, right, because 0 is divisible by 3. Now if a 1 comes, now what is your number, binary number? Now when you convert, so if you get a 1 after a 0, the number that you get is 1, so remainder is basically 1. So we'll go to Q1 because your remainder is 1. Now after a 1 you have two possibilities, you can get either 1 0 or 1 1. So what is the interpretation of 1 0? 1 0 is basically nothing but 2, because 1 into 2 plus 0. And you may also get a 1 which is 1 into 2 plus 1 which is equals to 3. So basically if you get a 1, you get 3, 3 is divisible by 3. So therefore on 1 you will go back over here, on 0 you will go to Q2. So this is how you are using the approach here, right? Now over here if you see, right, now Q0 is there, Q1 is there, Q2 is there, everything is with you. Now you are at Q2, you have got 1 0. What if you get another 0? You already know 1 0 is nothing but 2. If you get a 0 after that, what will be the interpretation? 2 into 0 plus 0, which is nothing but which is nothing but 2 into 2. The representation is 2, sorry. 2 into 2 plus 0, you are going to get 4. 4 is divisible by 3. 4 is giving the remainder of 1 when divided by 3. Similarly, if after this 1 0 you are going to get a 1, you will get 2 into 2, because for 2 for this one, 1 0 has already been interpreted as 2. So 2 into 2 is 4 plus 1 is nothing but 5. 5 when divided by 3 gives you a remainder of 2, right? Let's see. 1 0 0. 1 0 0 should give you the remainder of 1. So I will come here. 1 0 1 should give you a remainder of 1, right? 1 0 0, sorry, 1 0 0 should give you a remainder of 1, right? 1 0 0 gives you a remainder of 1, and 1 0 1 is nothing but 5. So 4 is giving you the remainder of 1, right? Now 1 0 1 is basically nothing but 5, right? 2 into 2, 4 plus 1 is 5. 5 is giving you the remainder of 2, so you will remain over here itself, right? Yes, yes. So is there anything left? For Q0 I have told the transitions on 0 and 1. For Q1 I have given the transitions for 0 and 1. For Q2 I have given the transitions for 0 and 1. So this will be my automata. Now you give any string to it, it will be able to interpret, don't worry. Like for example, if I give it 1 0 1 0, 1 0 1 0 is nothing but 10. 10 when divided by 3. 10 when divided by 3 gives you remainder of 1, right? 10 when divided by 3 gives you a remainder of 1. So it is 1 0 1 and again 0. So you are reaching to Q1, which is showing the remainder as 3. Are you getting this point? So you start it for the smaller strings, it will itself adjust for the larger strings, right? I always suggested you start with the smallest string in the language and then you start completing the DFA. Through that you can solve it, right? So now let us see another one. 1 0 1 1. 1 0 1 1 is nothing but 11. 11 percentage 3 is going to give you 2, modulus 2. Divided by 3 the modulus. So it is 1 0 1 1, you will state at Q2. And let's take another one, vowel 1 0 0. So it is 12 percentage 3 is going to be 0, 1 1 0 0. So 1 1 0 0 you will stay at Q0. 1 1 0 0 you will stay at Q0. Are you getting the point? Right? So this is how you will solve this. Now what is the short trick? What is the short trick? The short trick is very simple. When you are interpreting a number in any n-ary number system, so what will be done? In general, the questions will have an n-ary system. Either the system can be binary, it can be unary, it can be ternary, it can be quaternary, it can be octal, it can be hexadecimal, anything can be there. So number system will be n-ary, and then you are going to divide the number with some divided by m. So this is the generic case. So what is the short trick for this generic case? The short trick is very simple. You will place all these states. So divided by m, you will have m states q0 to qm minus 1. So you will place all these states on the rows. You will use the transition table to represent this transition. So again, DFAs can also be represented using a transition table. How? How do we represent DFAs using a transition table? Let us try to represent this. So I'll get back to this point later. Let me represent this DFA using a transition table. Let us draw the transition table. In transition table, I will place Q0, Q1, Q2 over the rows, and Along the columns, I will put the transitions. Along the columns, I will put the symbols. So how many symbols I have? 0 and 1, 2 symbols are only there. 2 symbols are only there. Right? 0 and 1 are the symbols. And Q0, Q1, Q2 are my states. Right? So I will say Q0, Q1, Q2 are my states. The states will come over here. So these are going to be your states. And these are going to be your transitions. So these are your states, these are your transitions. Sorry, transitions will write over here, these will be your symbols. Input alphabet basically. Right? Now you see Q0 on 0, where it is going? Q0 on 0, it is going to Q0 itself. Q0 on 1, it is going to Q1. Q1 on 0 is going to Q2. Q1 on 1 is going to Q1. Q1 on 0 is going to Q2. Q1 on 1 is going to Q0 again. Q2 on 0 is going to Q1. Q2 on 1 is going to Q2 itself. Right? So this is basically you have represented the transitions. So what is the 5 tuple? What is the 5 tuple for a DFA? A DFA. So what I'm claiming is a DFA can be represented using a 5 tuple. That is Q sigma delta Q naught F. And what I am claiming is this 5 tuple is itself shown over here in this transition table. That is how DFA can be represented using a transition table method also. So what are your states? It is written Q0, Q1, Q2. What is your sigma? 0, 1. What is your delta? This is basically delta. Q0 on 0 goes to Q0, Q0 on 1 goes to Q1. This is your delta. What is your Q0? Initial state, you will mark the initial state with an arrow. What is your final state? You will mark the set of final states with asterisk. So all this information, that is Q cross sigma delta, Q sigma delta Q naught F, can be captured in this transition table also. Are you getting this point? This entire information of Q sigma delta Q naught F can be captured in the transition table also. Right? And now let us come back to n-ary number system, which is, and further, that is divided by m. Now in this case, if you see, you have a binary number system and you are dividing it by 3. So the number system is a binary number system and you are dividing the number by a 3. So this is the specific case. In general, it can be a generic case. Right? So what you will do, you will write down the states. So how many states will be there if you are dividing by m? Q0 to Qm minus 1, m states will be there. The m states will come along the rows. Right? And the number system is n-ary. So how many symbols will be there? N symbols will be there from 0 to n minus 1. So these n symbols will come over along the columns. The size of the matrix will be, the transition table will be m cross n. How will you fill the transitions? You will start filling left to right, top to bottom in a zigzag manner. Q0, Q1, Q2 up to Qm minus 1. Then you will, in a circular manner, you will write the states. So you will go from left to right, top to bottom, and you will fill the states in a circular manner. How come? Let's see this example. You are saying that divide by m. Divide by m, in this case your m is 3. So you have 3 states, 0, 1 and 2. Right? You have an n-ary number system. When the number system is n-ary, what does it mean? That you have 2 symbols. In this case, you have a binary. So n-ary number system, you will have 0 to n minus 1 input symbols. In this case, it is a binary number system. So it will have two possibilities, 0 and 1. So they are placed over here. Now how will you fill the table? Left to right, top to bottom, in a circular manner you have to fill Q0. Q0, Q1, Q2, the states, then Q0, Q1, Q2. Why I am saying circular? After that, after you complete Q0, Q1, Q2, you again start with 0. So in a circular way, you are going to fill the states in a zigzag manner, right? You will start with Q0, Q1, Q2, then Q0, Q1, Q2 again, right? So left to right, top to bottom, left to right, top to bottom, so you have left to right and then top to bottom. This way you will fill the states in a circular manner. That is, once the states are over, Q0, Q1, Q2, Q3, Q4, Q5, whatever it is, how many number of states that you have, in this case 2, so therefore you stop at 2 and then start again with 0. So in a circular manner you are going to fill it, right? So you can apply this on any n-ary number system where divisibility is by m. So in that case, when n-ary number system is there, you will have n symbols 0 to n minus 1. When you are dividing by m, you will have m possible remainders, that is 0 to m minus 1, q0 to qm minus 1, you will have the states. And then in a zigzag manner, you are going to place, zigzag manner is left to right, top to bottom, you are going to write q0, q1, q2 and any number of states, q0, q1, q2 up to qm minus 1. Then again q0, q1, q2, q2, q3 up to qm minus 1. Again q0, q1, q2 up to qm minus 1 unless you fill all the cells. So this approach you can apply, and you can see this is getting followed over here in this example, and it will follow in all the examples. So where this technique is useful? When you have an n-ary number system which is divisible by m, right? So it can be applied anywhere. Now let's move to the next question, which says that construct a minimal DFA which accepts set of all strings over sigma equals to 0, 1, which when interpreted as a binary number is divisible by 3. The same question, but what is the assumption now? What is the assumption now? What is being said at assume that epsilon does not belong to the language. Earlier we had assumed that epsilon belongs to the language. Now we are assuming that epsilon does not belong to the language, right? Now if epsilon does not belong to the language, then your start state cannot be the final state. There needs to be done we need to do a small change, and what is that small change? That is what we are trying to discuss here. Is it making sense? What is that small change? That is what we are trying to discuss here, right? So now you just try to see, you just try to come up with a solution to this problem, and then we will discuss the. So you just try to solve it. How many states will be there? What will be the change in the DFA? What will be the change in the DFA now? With the change in the DFA now. So how many states will be there? How many final states will be there? So how to change the DFA now? That is what the question is. So that epsilon does not belong to the language. So this problem is only coming when you are saying divisible by 3. When you are saying when divided by 3 the remainder is 1, this problem is not there, because we are not accepting epsilon in that case, because the second state will be the final state. When I am saying when divided by 3 gives a remainder of 2, in that case the third state will be the final state. I am not accepting epsilon, so this problem will not come in that case also. But when I am saying when it is divisible by 3, I am assuming that the initial state is final state, I am accepting epsilon, and if the question specifically says that that epsilon does not belong to the language, what should I do? What should I do? That is the question. Let me give you 1 minute to solve this, and then I will discuss the solution for the same problem. I hope the problem is clear. If the problem is unclear, please let me know. So let me you solve it for in the next 1.5 minutes, and then we'll discuss the solution. what should the question is, how should we change the DFA now? Last 15 seconds guys, then I'll solve it. Can you tell me what should be the change in the DFA now? Okay, so I think let me answer it for you now. If you see this question, what is said, epsilon does not belong to the language. So I'll add another state. So let me bring that DFA here, and then I will do the changes in that DFA itself. Okay, merged with this one. Just a second. Okay. So now I am saying that epsilon does not belongs to the language. What should I do? What I will do is I'll create another state. This state itself remains the starting state. I'll create another state which will be my new initial state. This state itself remains the final state. And this is my new initial state, and in this state, which is Q naught dash, in this state epsilon is not getting accepted because this is not even the final state. This is not the final state. So Q naught dash is basically my new initial state. Now how will I write the transitions of Q naught dash? Simple, straightforward, the same transitions. It will follow the transitions of Q naught, right? So Q naught dash, Q naught on 0 goes to Q naught dash will also goes to 0 on Q naught. On 0 it will go to Q naught. On 1 Q naught goes to Q1, so Q naught dash will also go to 1 on Q1. Now this problem is solved. Now this language does not accept, this DFA does not accept epsilon. So to avoid epsilon, what I have done is I have created a new state which is known as Q naught dash. I have created a new state which is known as Q naught dash. So what I have done is I have created a new state which is known as Q naught dash. If my Q naught dash is my new state, new initial state which is Q naught dash, and which is not the final state, in that case epsilon will not be accepted, because we know that to get the epsilon accepted, the initial state has to be the final state. In this case it is not so, so therefore this is the right one, right? And it will follow the transitions of Q naught only. So for every DFA we can again apply of the type n-ary number system divisible by m. We can follow the approach that we discussed. I call that approach as zigzag approach. It's up to you, you can name it any approach. You can follow the zigzag approach, because why zigzag approach? Because of the format. You go left to right, then top to bottom, left to right, top to bottom, left to right, top to bottom. I am calling it as zigzag approach. You can follow the zigzag approach and then you have to fill the states in a cyclic manner. But in case epsilon does not belong to the language, then you will have to create another state, and you take the transitions of that state from your initial state, from your earlier initial state, right? This is how you will solve it, right? So I hope the solution is clear, right? Now let us move to the next question, which you have already done, that is, construct a minimal DFA which accepts set of all strings over sigma equals to a comma b such that the string starts with an a. I want that the string should start with an a, right? Now if I want that the string should start with an a, what should I do? I have already discussed the solution for the same. Why I am discussing this again? So as to come to a common conclusion, a good new conclusion. So for this you have already drawn. I will redraw it faster so that you so that we don't waste much time on this example again. So when you get an a, you should go to the final state. It is starting with a, and after that anything can come. But if it is starting with b, you will go to a dead state which is known as q2. You will go to a dead state which is known as q2. So this will be the DFA. So this is the DFA for starting with an a. Now if I change the question to ending with an a, now this is a new one. So why rediscuss the starting with an a DFA example? Because I want to conclude something. You wait for some time, we'll discuss the conclusion. Now ending with a. Let me give you some 1 minute to solve this. So again, let me read out the question. Construct a minimal DFA which accepts set of all strings over sigma equals to a b such that the string ends with an a. How to solve such questions, right? So how to draw the DFA for the same? Can you draw the DFA? We'll see, right? So let me give you the timer for 1 minute. Let's see who can solve it. Okay, the time is up. So how to solve it? Any answers? So you are saying ending with an a. So let us assume that, again let us draw the DFA for the smallest string in the language. A is accepted, so I will accept a. Now let us complete the DFA. Single a is acceptable. Now if you get a b in the beginning itself, you will keep on staying over here. Once you get an a, then you will say that my end has reached, the string's end has reached, so you will accept it. But in case if you keep on getting a after that also, then also you are in accepting state. But if you get a b, then you will again come back to the initial state which is q naught. Why? To say that again I am not ending with a, I am ending with b. So this state is representing ending with b. This state is representing not ending with a. This state is representing not ending with a. This state is representing not ending with a. This state is representing ending with a. Right? This is how you can draw it. So what we noticed in the ending DFA, we had a loop back. What is this loop back doing it? You assume that your end has reached, your string's end has reached, and you are ending with a. But if a b comes back, you will loop back to the original state wherein you are not ending with a. Right? But if it is like a DFA which says starting with something, in that case you will always have a dead state to represent those states which are, to represent those things which are not starting with what you are saying, right? This is what seems to be the conclusion. We'll discuss it again. Let's say this one. When we say construct a minimal DFA which accepts set of all strings over sigma equals to a comma b such that the string contains an a. What to do in this case? Such that the string contains an a. Right? Construct a minimal DFA which accepts set of all strings over this which contains any. So let me give you a timer for 1 minute to solve this, and then I'll discuss the solution. And once we discuss all these three examples, containing a, starting with a and ending with a, then we'll conclude what is the general pattern of these DFAs so that you can draw them faster. So can you tell me the number of states as well as the number of final states in this DFA? Okay, anyone able to solve this? I think enough time has been given. Let me solve it now. So when I say construct a minimal DFA which accepts set of all strings over sigma equals to a comma b such that the string contains an a. So when I say contains an a, so as soon as I get an a, so smallest string which is acceptable is a. So I will make this DFA. Then I will complete it. If I am only getting B's, I will be saying over here, once I get an A, it means I am accepting. After that, if I get anything, I will remain at AB. I will remain at this state. This is Q0. This is Q0. This is Q1. This is Q0. This is Q1. And we are done. That's it. Once you get an A, you reach to the final state. After that, whatever comes, you don't care at all. Right? So therefore, this is your final DFA in this case. Right? Now, what is the conclusion? The conclusion is, when you have ending with something, there is a possibility of loop back. Why there is a possibility of loop back? We will assume that we are ending with that thing, and all of a sudden if something else comes, we will loop back to the original state. Now when I say contain a, okay? So ending with something we have discussed. When we say contain something, in that case there is neither you will have a loop back nor you will have a, let us discuss starting with something first. Starting with something, here you will not have a loop back, but you will have a dead state. What will that dead state represent? In this case, you will have a dead state. What will that dead state represent? That dead state is representing what if you are not starting with the something which you want. So therefore, you will always have a dead state to represent all those strings. Now, if it is contain a, contain something, in that case, neither you will have the loop back, neither loop back, no dead state. So here neither you will have the loop back nor you will have the state, right? If you go back and look at the examples, you see starting with A, you have a dead state or the trap state. Ending with A, you have a loop back. And then containing A, neither have a loop back nor have a dead state, right? So this is what we can conclude about ending, starting and containing, right? So now let us solve another interesting DFA question, which says that construct a minimal DFA which accepts set of all strings over sigma equals to a comma b such that the string starts with an A and ends with a B. Starting with A and ending with B. So this is what we want. Starting with A and ending with B, right? So let me give you some 2 minutes time to solve this and then I'll discuss the solution. You have to tell me the number of states and the number of final states. That is mod of Q and mod of F. Yes, what should be the answer? Yes, what will be the final states and what will be the total number of states? Okay, I think enough time has been given. Any answers, guys? Okay, so let me solve it. Starting with A, ending with B, right? So let us try to draw. Initially I am at Q naught. Once I get an A, my string is starting with A. If I get a B in the beginning, I will go to a dead state and stay over there because I want starting with A only. Now if it is starting with A, now the next check that I have to do is it has to end with a B also. Now if I get a B itself, that means that AB is the smallest string in the language, it is accepted. Now if after A and B, if I get an B again, it is again ending with B, but if I get an A again, that means that I am not ending with A, there is a loop back. Because of ending there is a loop back, because of starting there is a dead state. That concept that we discussed is being used here. Now when I say when I say on this state, I know what to be doing, what is to be done on B, but if I get an A over here, I'll stay on Q1 because I am waiting for a B to get accepted. I'm waiting for a B to get accepted, right? So this state represents starting with B. This state represents epsilon. This state represents starting with A. This state represents ending with B. So that is how, what is the meaning of each state. Now let us say that so how many states are there? Q1, Q2, Q3. So how many states are there? There are 4 states, and what is the number of final states? 1 by 4. 25% of the states are final states, right? This is what we have discussed. Now, is there another approach of solving this? We know starting with A DFA, we know ending with B DFA. What is being asked is you concatenate starting with A with ending with B. So language 1 is, let me tell what I am trying to say. I am saying L1 as starting with A, L2 is ending with B. Can I say the language which is saying that L3 is starting with A concatenated with ending with B, right? That is L1 dot L2 is L3, starting with A and ending with B. If you start with A and then after that you have to start with an A, and after that whatever are the strings in ending with B, if you merge the two, if you concatenate the two languages, you will get starting with A and ending with B. Like for example, starting with A will have A, AB, A, and so on. Ending with B will have B, B, AB, then say AAB, BAB, and so on. If you concatenate these two languages, so for example, A followed by the second language, A followed by B, AB is acceptable by this language. A followed by AAB, again accepted. A followed by double A, B, again accepted. A followed by BAB, again accepted. AB followed by B, ABB accepted. AB followed by AB, ABB, ABAB, again accepted. So again you have got this twice, ABAB you have got twice. But since it is a set, you can remove the repetition, you can remove the duplicate since it is a set. But this is like concatenation of the two languages. Can we do something on the DFAs in this way? Yes, we can definitely do that. Let us try to construct the DFA for starting with A. Starting with A DFA, right? Now let me make the DFA for ending with A, ending with B. This is starting with A. Now ending with B is ending with B I want is this one. Now what I have to do is to concatenate these two DFAs, and what is the approach? What is the approach? The approach is very simple. You will take the initial DFA, and then after that, instead of going to the final state of this DFA, you remove this final state and then directly jump to this DFA. Right? You remove the final state of DFA1 and to DFA2, you go directly to DFA2's initial state. So what you will get is the same picture that we drew earlier. A and on B, so on A you are going to this state. So what will be the final DFA? If you see this, you are going to remove this from here, and what you will get is, just a second, and all this will go and you will directly go. Now if you compare it with what we made earlier, it's exactly same. On B you are going to this state AB, on A you are going to this state in which there is a transition on A, and on B it is going to Q2, A and then B, exactly same, right? So are you getting this point? So what is understandable here is you can do also the concatenation of the DFAs the way we discussed. Now let's see another question. Here we have said that it starts and ends with starting with A and ending with B. What if I say that it says that, what if I change the statement, it starts and ends with a different symbol? If I change the statement to this one, starts and ends with a different symbol, if I change the statement to this one, what will be the change in the DFA? That is what I want to discuss. Okay, so let me set the timer for 2 minutes for you guys to solve it. And then we'll discuss the solution. Okay, the time is up. What we are saying is starting and ending with different symbol. So what we did earlier is starting with A and ending with B. That will remain itself as it is. Now the extra thing is starting with B and ending with A. So the one which we made as dead state now also have similar transitions just like the starting with A and ending with B. That way we will make it, right? Let us see. Starting with A, this is starting with B. Earlier we made it dead. Now we will not make it dead. Now it should end with B. So AB is accepted, minimal string. And after that, if you get an A, you will come back over here. If it B, you will remain over here. Here, A will be there. Now over here, if you get a BA, you are accepting it. If you are again getting B, not accepted. If you are again getting B, unless you get an A, you will keep on waiting. Again, if you get an A, okay. If you get a B again, you will come back. Right? So this will be the DFA. So this part was not there in the previous case. Now it will be a part. So this was just dead. Now we have included both these things. So there are 2 final states out of the 5 states. What percentage of states are final? 2 divided by 5 into 100, which is nothing but 40%. So when we said regular languages are closed under union, intersection and complementation, okay, so we have three cases over here, three things which we have claimed. So how do we take the union thing? How do we take the union thing? How do we take the intersection thing? How do we take the complementation thing? Right? So how do we take union, intersection and complementation? That is what we are trying to discuss. So union, the approach we have discussed. How do we take union? We will, how will we take the union? It's very simple. How? We will take the cross product of the DFAs. If we have two DFAs, we will take the cross product of the two DFAs and the transitions will get from the original DFAs. The initial states will remain the same and the final states will be those states which are final in either of them. And in case of intersection, we will take those states which are final in both of them. And let's talk about complementation. Let's talk about complementation. Union is done, intersection is done. Complementation. Complementation, what we do is we will make the final states as non-final states and non-final states as final states. That's it. So that way we can prove that regular languages are closed under union, intersection as complementation. But this we have done for DFAs. With this we have not done for NFAs and epsilon NFAs. So how can we say this? We will prove that. We can easily prove that all these three are equivalent in power. So that means that every NFA can be converted to an equivalent DFA, every epsilon NFA can be converted into an equivalent NFA, right? So since their powers are similar, if we have discussed, their powers are almost similar. So if we have discussed something for, DFAs, it is also applicable to epsilon NFA and NFA. Why? Because their powers are same. But that does not mean that I will be able to apply the same algorithm of union, intersection and complementation over NFA and epsilon NFA. I have to convert NFA and epsilon NFA to a DFA and then only I can apply these algorithms. But since they are equal in power, they are convertible to each other. Are you getting this point? Is it okay? Yeah. Now the last point, again for concatenation also we have done the same thing. So I can say they are also closed under concatenation also. They are also closed under concatenation also. Right? Okay. So again, let me reiterate, you cannot apply these algorithms directly on epsilon NFA and NFA, but you can convert every epsilon NFA and NFA to a DFA and then you can apply these algorithms. So we can say that regular languages are closed under union, intersection, complementation and concatenation. Right? Yeah. Right. So that's it. So again, in this session, what we discuss is some advanced questions on some more interesting and advanced questions on DFAs we have discussed in this session, right? Now that's all about DFAs. In the next few sessions, what we will do is, so we have already done with 4 sessions. In the first session, we discussed introduction to TOC. Therein we discussed the importance of the subject as well as the applications of the subject. That is what we have discussed, right? Then we discussed deterministic finite state automata. We introduced the concept. In the next 2 sessions, we did some interesting questions on DFAs. And then we'll have the next session in the next week on 30th of May, wherein we'll discuss the concept of minimization of DFAs. What does that mean? That whether the DFA that we have got is basically, for example, the DFA that you have got has higher number of states. If you want to minimize it, if you want to get the minimal DFA, is there an algorithm for the same? Yes, we have an algorithm for the same, and that algorithm we are going to discuss on 30th of May. Right? So we'll discuss the minimization of DFAs in the next session, right? I hope you are clear with the concept of DFAs and you have a good hand on DFAs, you are able to understand the concept of DFAs, right? Now we will start with minimization of DFAs in the next week. That's all for this session. I will see you guys in the next session on minimization of DFAs on 30th of May. The timings will remain the same, that is 4 p.m. to 5:30 p.m. Right? The timings will remain same, that is 4 p.m. to 5:30 p.m. All right. So I'll see you guys in the next session. Yeah. Thank you guys.